So greetings students. So in last class, we have dealt with the structure of the power system concept. Okay, we have seen about the structure of the power system, and in today's class we'll be moving with the its continuation. Okay, so mainly in the today's class, what we'll be dealing with your per unit system. Okay, we'll be dealing with your per unit system. Okay, we'll be dealing with your per unit system. So first you have to know about the concept of single line diagram. Okay. So yesterday at the end of the class, I have shown you a MATLAB model, Simulink model of a 3-bus, that is a 3-machine 9-bus system. Okay. It had nearly 3 system for generation purpose, and it was a interconnect. It was an interconnected network with a 9-bus. Okay, it had 9 bus with it. Okay, so in while I was showing that model, some of the students asked about the components of it. Okay, so in general, the component of a transmission network can be expressed in the form of a single line diagram. Okay, about the single line diagram, you might have already studied in your transmission and distribution subject. As I said in the previous classes, in the single line diagram, there will be generation part, there will be a transmission part. Okay, after that there will be a load, that is the consumer loads. Okay, so here you can see the generation part is generally represented in this fashion with a circle. So what does it means? It means a machine. So generally this represents the generators. This represents the generators. So after this kind of winding represents a transformer, and in this there are 2 types. First one is a 2-winding transformer, and the second one is a 3-winding transformer. After this there will be a circuit breaker CB. Okay, and the configuration of the transformer will be represented in this fashion. So if it is represented in like this, means this represents that the primary of the transformer is in the star configuration and the secondary is in the star configuration. So this is the representation. Okay, at the same time, over here you can see, here it is a star, and then this represents the delta. Okay, this represents the delta. Okay, so these are the components related with your power system network. So in the power system network, generally you can normally take this as a blueprint for an interconnected system. Okay, this represents as a blueprint for an interconnected system. And now we'll be moving to the next important topic of per unit normalization. Okay, so what do you mean by per unit? Have anybody heard about this per unit system before? Anybody know about this per unit system before? Or you are hearing this as a new word? So here already they have given, this represents a per unit normalization. Okay, normalization. So what is meant by normalization? So anybody know about the normalization or the concept of per unit? So if you know, you can just even type in the chat box. So nobody know about this concept, right?
Yes, sir.
Okay, fine. Okay.
Sir, per unit means fixing one value and calculating another value with respect to the standard value. Sir, fixing one value as a standard value
Yeah,
and
sure.
calculating the parameter with respect to that value. Sir.
Of course, of course.
Example, normally percentages are examples of per unit, sir.
Yeah, correct. You have given a correct answer. The thing is that we are normalizing. Okay, as he said, we have to keep a certain value as a reference. Okay, you have to take a certain value as a reference. So, for example, I can give a practical example itself. Okay, so you can take so at the end of your final year, you are eligible to write your GATE exams. Okay, you can apply for your GATE exams at the end of your final year. So in the GATE exams, at the end of the GATE exam, your results will be based upon normalized percentage. Okay, it will be based upon a normalized percentage. That is how they will be putting out the rank and the marking system means they will be taking the topmost candidate mark. They will be taking the topmost candidate mark. For example, the GATE exam you will be writing for nearly 65 marks. Okay, you'll be writing for 65 marks, and after of this 65, if a candidate A is scoring around 42 marks in the sense, 42 marks in the sense, this mark is taken as the reference, and based upon this reference, they will be calibrating other marks. Okay, they will be calibrating other marks. Okay, I hope you can catch the point. So why we are doing such kind of normalization means it will be easy for giving the score. Okay, it will be easy for it is some kind of a easy ranking system. Okay, you can easily rank each and every student based upon the reference mark, and you can easily avoid any kind of confusion. So apart from GATE exams, TANSET also follows such kind of strategy. Okay, I hope you might have understood a little bit. So okay, coming to the power system. So as I said, we are dealing with an interconnected system. So in yesterday's class, we have seen about a 3-machine 9-bus system. Okay, so there were 9 buses in that system. So these 9 buses will be some of the bus will be having a rated voltage of 210 kV. Yesterday itself I have shown you that, and some of the bus will be having a rated voltage of 11 kV, and some might be having about 66 kV, and even some might be having around somewhere around 44 kV. Okay, this are all possible voltage ranges in the interconnected power system network. Okay, and hence it will be a very difficult and a tedious task to have a eye over all the voltages. Okay, so for that thing, in order to have a constant monitoring of each and every bus, one bus voltage will be kept as a reference. One bus voltage will be kept as a reference voltage. Okay, so based upon this reference, they will be calibrating all other buses. Okay, for example, you can take the second bus is, if it is taken as a reference, means apart from the second bus, all the other buses will be based upon the base value of this second bus. Okay, that is, all the other buses will be represented in the form of the value of the second bus. So in dealing the problems, you can easily understand. Okay, so for example, here they have given a tabulation. So if you just see through, that is, they are normalizing it. How they are normalizing, they are given. So I'll be moving with it while giving the example problem. I'll be showing it. Then you can easily understand about the per unit concept. Okay. Coming to the per unit system, here is the definition. This is the definition of the per unit system. So it is nothing but an interconnected power system. This is the main important point you have to take. So you'll be considering the interconnected power system network. Okay, as I said, it will be having many different level of voltages, because at each stage you will be stepping up or stepping down of your voltages using your transformers. So next, for the simplicity of representation, the per unit system simplifies the complexity of the power system. Okay, so for that you will be choosing the reference or the base parameters you will be choosing, and there are some certain criteria for choosing such kind of base parameters. So I'll be telling out what are those criteria, and the different voltage levels disappear, and overall system reduces to a set of impedance based upon the per unit system. If we are using a per unit system, the main important advantage is that the complexity reduces drastically. The complexity of the power system network reduces drastically. Okay, so moving on. So this is the definition of the per unit system. So if you want, you can just note it out. This is the common formula. So based upon this formula only, we'll be defining the per unit for each and every bus. So what is the formula? If you're taking out means, so the formula is that quantity per unit. Okay, so this is the thing what you have to get. Quantity per unit is the value that you have to get. So how it is obtained means, quantity in terms of normal units. Okay, next is the base value of quantity. Okay, this is the representation.
Sir, can you tell what's the difference between the normalization and the per unit system, sir?
No, normalization, that is per unit comes under normalization. It is a type of it is a method for normalizing. Okay, the normalizing method that we are using in the power system area is generally called as per unit system. Okay, this is a basic definition. So I'll be moving to the next part, then you will be getting somewhat a clear idea. Okay, first the thing is normalization Based upon normalization, one of the method is only your per unit system, which is used in your power system network. So here you can see so we can take the previous example itself. As I said, we'll be taking the bus 2 value as the reference means or the base value means. Here they'll be calling it as a base value. Okay. Then all the other bus will be represented in such kind of per unit. That is, for example, here you can take, so bus 2 is the base value. Then if you want to represent the bus 1 in terms of the per unit means, what we'll be taking is V per unit will be equal to the actual voltage, okay, the actual voltage of the V bus 1 divided by the base voltage. Divided by the base voltage is nothing but your bus 2 voltage. It is just a representation only, because we will be dividing all the buses. We will be dividing all the buses in the network with the base value. Okay, that is, you will be converting your entire thing in terms of some integers. So this per unit will be in terms of integers, in the sense it takes the value from around, maximum it will be taking from 0 to 10. Okay, so it will be a very easy method of representing your network. Okay, I hope you might understand this. Okay, so the same thing is used over here. So for the current, you'll be taking the current of the bus 1, that is I bus 1, divided by the base value is nothing but the I bus 2, this value. Okay, so here this base value you have to represent, if you are representing the base value, per unit for the bus 1 means, you have to consider all the other parameters also, like your apparent power followed by your impedance. Okay, so here the base value of the current, so base value of voltage remains the same. Okay, remains the same. In most of the case, you can find it out in the question itself. They will be giving you the base value, but the current base value they won't be giving out. They'll be giving the rating of the power rating they will be giving. It is you who have to find out the current base value. So the current base value can be found like this. So I base will be equal to S base divided by B base. Okay. Next is about the impedance. So impedance is nothing but it is normal Ohm's law. So V equal to IR, the same law is used here. So if you know the value of the V base and then I base, you can generally calculate your Z base. So apart from this current, okay, apart from the current, you can also represent Z base in terms of the power quantity. So it is nothing but the V base by S base. Okay, this is what with respect to what you can say the power ratings, per unit. So now we'll be moving on. So this is the formula of the per unit quantity. So the per unit value is generally nothing but actual value by the base value, as I said. So you know about the base value and the actual value. The base value is the thing what we will be selecting out, what you will be selecting. Okay, the base value is what we will be selecting, and the actual value is the one that will be converting for the respective bus. Okay. So here they have given in terms of kilovolt. So this represents your apparent power. So this represents your apparent power S. This represents your voltage. This represents your base current followed by the impedance. Okay. So here you can see the same formula is again repeating over here. So generally we will be speaking in terms of kVs. Okay. In the transmission line, we will be generally representing the voltage in terms of kilovolt, and hence the power will also be in kilovolt amps. Okay. So the impedance is given by kVb by Ib into 1000. Okay. So generally it is a normal Ohm's law, and this ZB is in terms of the power representation. Okay, that is kVb square by MVA. So these formula and the formula that we have seen over here are the same. Okay, this formula and the formula what we have seen over here are the same. So if you want to represent in the per unit impedance, then it is based upon actual impedance by the base impedance. Okay, I hope you might have got some clarity on per unit system. So now coming to the three-phase representation of the per unit system. So the first one is the three-phase. As you know, there will be line voltage and phase voltage. So if you are considering a balanced voltage, okay, then over here for representing your voltage will be voltage in per unit, you can either consider the line voltage or the phase voltage. Why in the sense means, if you are considering the phase voltage actual value, so this is the actual value, we are considering this actual value mean in a phase representation, then it is mandatory to represent the base value also in your phase representation. Okay, I hope you are understanding, because it is a ratio. Your per unit is nothing but a ratio. Okay, for that purpose only, either you can take both the things as in your as a phase voltage, or you can take it as a line voltage. So coming to the next point, and over the calculation for the base current, so this is the base current.
Sir, your voice is breaking, sir.
For three phase, so it will be
Sir,
impedance also. Having some connectivity issues over here. Okay. So now I'm able somewhat.
yes, sir.
Yes, sir.
I hope it's clear. Okay. Okay. Yeah. So coming to the three-phase system, the base value of the current over here, it will be divided by the √3 component. So and the same thing goes for your impedance also. Okay. and the representation of the final impedance in per unit is will be going like this. So this is the main formula that we'll be using in the problems. Okay, so while going with the problems, you'll be understanding very easily this per unit concept. Okay, so if you want to find that is as I said, you can take bus 2 as a reference. So if you want to find the Z impedance for bus 1 means, if you want to find the Z impedance for the bus 1, so ZPU dot 1. Okay, ZPU dot 1 if you want to find means, so this will be going like this. So ZPU old value, okay, into KVB old value. KVB is nothing but the, for example, this we can easily represent like this. So ZPU for your first bus, you can write as ZPU. So old thing you can take it as the bus 2, okay, for the bus 2 into KVB. So old is nothing but your second bus. So 2 divided by KVB 1 the whole square into the same thing will be representing in the terms of your apparent power MVA. So it is B MVA is new, right? So new means 1 divided by MVA B2. So if you are knowing only this formula itself, it is very easy for you to represent the impedance. So if you are finding the impedance, then you can easily draw the impedance diagram. So impedance diagram is nothing but it will be more or less similar to the single line diagram, except that it will be represented with respect to the impedance. I'll be telling you how we can draw the impedance diagram in the upcoming class. Okay. So again, here it is general components of the power system. So here you can see this is the equivalent circuit of a generator. Okay, this is the equivalence circuit of a generator. As I said, with respect to the reactance diagram, so if you want to convert this generator into the reactance diagram means you have to convert like this. In this fashion, you have to convert. Okay, that is generally you will be eliminating this RA. Okay, generally you will be eliminating this RA. The same thing goes for your synchronous motor, but the thing is that for the generator, the current gets applied. So this is the main important thing you have to see. For generator, the current gets applied, but at the same time, if you're considering a synchronous motor, so this acts as a load. So the IA will be flowing inwards. Okay, for the generator, the IA will be flowing outwards, that is the current. As for the synchronous motor, the IA will be flowing inwards. Okay, and this is the equivalent circuit. So the equivalent circuit will be more or less equal in case of your generator and your synchronous motor. So coming to the transformer, as I said, in most of the case when representing your reactance diagram, your resistance part will be omitted. Okay, and it's the same goes for all the other components also. You can take even the transmission line, and this is what with respect to the load. Coming with to the advantages of the per unit representation. So what is the primary advantage of this per unit representation in the sense? This gives a valuable relative magnitude information. So the interpretation part is very much simpler if you are using a per unit representation. Okay. Circuit analysis of systems contain transformers of various transformation ratio is generally simplified. So this is what I have said. So in most of the cases, the turns ratio in the transformer will be differing at each stage of the interconnected power system. For that purpose, generally what we'll be doing is that we will be making use of the per unit representation. Okay. So after this, the circuit parameters tends to fall in relative narrow numerical ranges, making ergonomous data easy to spot. As I said, it will be in terms of integer values. Okay, it will be in terms of integer values, mostly from 0 to 1. So this is the main data range you can see. Okay, it will be 98%, it will be from 0 to 1. The per unit value will be ranges always from 0 to 1. In some cases, it might go around up to 3 to 4. So those are some exceptional cases in the power system network. Okay, the per unit system are ideal for computerized analysis. So this is the main thing. We will be seeing about this in the second unit. It will be more easier for the ideal for computerized analysis. So yesterday I have shown you the MATLAB model. So in that MATLAB model, I have entirely converted the system to a per unit system. So I have kept one bus as a reference. So based upon the reference value of the bus, all the other buses will be interpreted. Okay. So next is manufacturers usually specify the impedance values of the equipments in per unit data of the equipment rating. So this one is with respect to the power system components. In most of the substation you can see. So there will be representation of electrical quantity in terms of the per unit. Okay. Also, if you are representing the per unit value, it is possible for you to easily assume in some numerical calculations. So we will also be assuming some per unit values, but it will be coming in under the fourth unit. We will be seeing it. So the ohmic value of the impedance as referred to the secondary is different from the value as referred to the primary. But the base values are selected properly. So here this is the main thing. So if you are selecting the base value, okay, if you are selecting the base value, it is the thing that you can omit the ohmic values while they are representing in your reactance diagram. So this part will be somewhat confusing to you. So I'm not going deep into it, but while solving the problems, I will be surely telling you about this part, sixth part. Okay. So now we will be dealing with the procedure to obtain the impedance and reactance diagram. So if you want, you can just note it down, and soon I will be putting the notes and the PPT. And as I said, so this is the single line diagram that you have to see through. So this is a single line diagram. Here you can see. So can anybody say, based upon this single line diagram, can anybody say how many generators and how many loads are there in this system? Based upon the single line diagram, you can just see through it, and you can say how many generator section and how many loads are there.
So 2 generating sections, sir.
Okay, fine.
And then there will be 3 loads, sir, including the motor.
So sorry, I have just disconnected. So can you come again? So 2 generators.
Sir, there will be two generators and there will be 3 load including the motor,
Yeah,
sir.
yeah, of course, you're correct. There is nearly two sources and 3 loads, including your motor. So you're correct. And over here, the representation is such that it is a star connected. It is a star connected. So it is a star. It is a delta. It is a delta. It is a star. It is a delta. So this representation of star and delta, you have to be very much careful over this transmission line. So because while solving problem, many of you will be doing some mistakes in this transmission line part. So they'll be taking out this star, and then they'll be considering this also to be a star. And generally what happens, they'll be losing a √3 component in the problem. Okay, so you have to be very careful about this configuration also. Okay, so now moving on to the procedure, how you can represent this single line diagram in this kind of impedance diagram. So this is the impedance diagram, and this is the reactance diagram. So basically in your reactance diagram, you will be omitting your both resistance and capacitance. That is, if you are neglecting your resistance and capacitance in your impedance diagram, it is possible that you will be getting your reactance diagram. Okay, that's the single thing you have to consider. And how you can convert such kind of single line diagram into this fashion. Okay, so I'll be just completing up to this, and can just take it out. Okay, so the procedure for drawing the impedance diagram is over here. The current limiting impedances are neglected. Okay, and so while solving the problem, you can easily understand the shunt component of the transformer is neglected. Mostly this kind of impedance diagram and the reactance diagram revolves only around assumption. Okay, the power system, most of the component will be revolving around assumption. So there will be some set of rules like your Thevenin equivalent circuit and Norton's equivalent circuit. There will be some kind of specified rules, right? You will be open circuiting your capacitor component, will be short circuiting an inductor component. So there are some set of rules. Okay, similar to that, over here in the power system also, there are some set of rules for this impedance diagram and the reactance diagram. Okay, but in both the cases, what you have studied in your circuit theory as well as what you are studying now, both are just assumption only. Okay, both are assumption only. Okay, so you will be neglecting the shunt component of the transformer because I0 is less. Okay, if the reactance is greater than your R, that is this is what your they are saying, that is if the source reactance is greater than R, then R can be neglected. Okay, so how they are drawing this diagram in this fashion, in the sense, as we have seen, there are some equivalency. There are some equivalency for each and every circuit. Okay, so first you will be representing two generators. As you can see very clearly that these two generators, generator 1 and generator 2, are in parallel, right? So they are in parallel only, no? They are in parallel or series? Can just answer the question.
Parallel, sir.
Parallel, sir.
Yeah, they are in parallel. Why they are in parallel? The another way to find that they are easily represented in the parallel is that they are connected to a same bus. Okay, they are connected to the same bus. They consider this a bus 1 and consider this a bus 2. They are connected to the same bus. So while they are connected to the same bus, the voltage across the components in the bus will be the same. Okay, the voltage across the components in the bus will be the same. So what happens then? This G1 will be in parallel to G2. Okay, this is another kind of explanation. So you are representing this thing in this fashion. So there are two generators. Okay, this is this component represents your first generator G1, and this represents your second generator G2. Okay, I hope you are able to understand. And after that, you'll be coming across a transformer, right? So this is a transformer, and the equivalent circuit for the transformer will be this one, this version. Okay, and here you'll be having your transformer. So this is your transformer. Okay, followed by your transmission line. Followed by your transmission line. So here they are taking your transmission line. I think this is a pi-type transmission line because you are having two capacitors. Okay, so the transmission line here represented is a pi-type line, and after this, you'll be representing. Sorry, here this is a load. Okay, not transformer. So this is the load, and this is the transformer. Okay, this is the load. Okay, this is the load A, which is connected to this bus. As it is connected to this bus, immediately after the G1 and G2, you have to represent the load. Okay, and after this only you have to go for the interconnection, and the interconnected element first part is your transformer T. It is given here, and after this there comes your pi-type transmission line. Okay, this transmission line, and after that you'll be getting with your transformer again transformer, and after that you'll be getting with your load B, and finally followed by your motor M. So this represents your motor M. Okay, so this is the method how you can draw your impedance diagram. I hope you are able to understand it. Okay, and yeah, so coming to the next part, if the reactance diagram, as I said, in the reactance diagram, you'll be only calculating the reactance. So it is a very easy to that you can omit all other components. Okay, so here you will be omitting your capacitors, and then resistors you will be omitting, and finally this entire diagram will be a combination of your source and reactance. So over here the current limiting reactances are neglected, shunt component of the transformer is neglected, so it is already neglected over the impedance diagram. Okay, the resistances are neglected. Okay, so this is what with respect to the impedance diagram. I hope we can stop with this.
So in the reactance